Hello, it's Keith here, and this is the fourth of the YQuest series of 68,000 assembly tutorials. Today we're going to be looking at the Amiga, and we're going to be looking at the YQuest port to the Amiga system. Basically, it's based on the original Simple series, where we got a smiley moving around the screen. It's been now extended, and we've got this little game here, if I can just remember what the controls are. And here we go. So basically we're using bitmap graphics to draw the icons here, the characters here. So we've got the Y, which is the sort of player, and we have to collect these crystals. Now you'll notice that the horizontal movement's quite jerky at the moment, and that's because it's based on the original code, which was only working in full byte movements. So at the moment it's a little bit jerky, but a later version we'll look at in a later lesson will smoothen things up. But at the moment we're just based on that original Simple series where we had the smiley moving around the screen. Okay, well, let's go over to the code and let's have a look at the platform specific code for today's example. Okay, so here's the code here, and we're going to go through it in sections. We're going to go through the bits that we've covered before pretty quickly, so if you've not seen the Simple series, please have a look at the bitmap drawing and the joystick examples there, because I don't want to repeat things that I've said exactly the same as I've said them in the past. Now, you'll see there's a part marked collision mask X here. Now, the Y movement's very smooth, but the X movement's moving in those 8 pixel chunks. And because of that, we're masking the collision detection to make sure that objects that don't look like they're overlapping aren't considered to overlap within the logic of the collision code. So that's there as a limitation. As I say, there will be a version later that will have much smooth movement, which won't have that limitation. We're then defining the size of the screen here. Each version of the game works at different screen resolutions. This one's 40 characters wide, but some are just 32, so there's different code for those. We've got some definitions of control ports for the hardware here. And then we're setting up the graphics screen here and the palette for the game. Now, I'm not going to go over these again because we've covered them already in the Simple series. So this is just setting up our screen, and then the start of the new code is here. Now, the game uses a section marked as user RAM. It's at the bottom here in chip RAM. This is some variables. The game will, of course, have various variables for the objects, the player, the bullets. Each object has 8 bytes, and those define the position of the object, the acceleration, the sprite being used, and a few other things. So that's what those are. You'll also notice we've got some sound effects here. This game uses something I call chibi sound. It's a little sound driver for simple bleeps and bloops, and it needs a wave for the sound, for a beep, and for a noise distortion sample, which are used in the game. And you'll also see we've got the screen memory and the copper list here. Those are the same as in the Simple series, so there's nothing new in those. But we need to reset that memory just to make sure it's zeroed when the game starts. Once the memory is zeroed, we need to initialize for a new game. This happens every time the game restarts. So we set the lives to 3, 0, the score and the level. We set the player object sprite to 0, and then we silence chibi sound here, which uses the D0 register. Now we're going to show the title screen. Now you've seen the title screen. If I just start the game again here. This is the title screen here, and it's made up of 8x8 tiles. It's actually the sprites that are used by the game, just used us to make a picture here. Very simple. So we're loading in each tile from the tile map, the picture here. It's defined within the common code. There's various versions depending on the screen size, and we're checking each one, and if it's non-zero, then we're going to show it to the screen. Now, the sprites themselves are held as bitmap data. They're just here. There's 4 different versions of each sprite for 4 frames of animation, and also there's a font in the same format. So the sprite data here is the start of the memory that defines the bitmap graphics. Now, getSpriteAddress will calculate the offset within that sprite data for a numbered sprite. So this is calculating the memory address, and then showSprite is going to copy the sprite data onto the screen. So showSprite is doing the work of displaying it. GetSpriteAddress is calculating the sprite for the sprite number and the frame. Now we just repeat that until we've shown all of the tiles, and then we show some messages on the screen like the high score, the website URL, things like that. At the start of each level, the first level or any successive level, we wait for a fire button to be pressed, clear the screen, center the player and give the player some invincibility, and we initialize the level with the settings for the current level number. That's things like the crystals, the enemies, and so on and so forth. Okay, now here we've got the main loop. Now, read controls dual will read in from the joystick, and what we do is we set a default setting of no buttons pressed, and then if a button's pressed down, we alter that setting so that we can compare it later. Let's have a look at read controls dual. Now here it is. Now reading in the joystick, we've discussed it before in the simple series. It's a bit of a pain on the Amiga. Basically the ports are sort of analog and we need to convert them to digital. Fortunately there's some formulas. We just read in the bits here and then we use bit 9 XOR bit 8, bit 1 XOR bit 0 for up and down. Left is bit 9 and right is bit 1. And the fire button we read in from a different port, we read in from just here. Now it's a pain, but basically you can use this sort of formula as is, and that will get in the first joystick. If you want two joysticks, there was an example in the platform specific series where we covered using two joysticks, but that will do us the job of getting a single one for this single player game. So that's being used here to read in the joystick, and then we're just checking if a key's been pressed. If a key has been pressed, then we're storing it into D2. So D2 is now our button presses that we're going to check in a moment. Next we draw the text on the screen, the score, the remaining crystals, the lives, things like that. We then clear the player sprite off the screen because we're going to recalculate the location of that player sprite. Okay, so now what we're going to do is we're going to check the timeout. Now when you press up, down, left and right, you're not just moving the player, you're altering the acceleration because the player will keep moving in the same direction. Now if we don't have a timeout, the acceleration would happen too fast and it'll get out of control. So we're checking the timeout. If the timeout non-zero, we're going to skip over processing any continued holding of the joystick. If the joystick is being tested, we're checking each of the bits of D2, which we read in here with read controls dual. And if a direction is pressed, we're altering the acceleration here, and we're doing that just altering the player acceleration, making the player move faster or slower in either right, left, up and down directions. So that's what's happening there. Now here we're testing the fire button. If the player has pressed fire 1, then we're going to fire a bullet, and that's in the common code. If the player's pressed fire 2, we're stopping the player dead in their tracks, ceasing the acceleration. Bit of a handbrake there. Finally, we update the timeout. The timeout is set if the player has pressed a direction key, up, down, left and right, you can see here. Then once we've done that, we're just updating the movements of the game code. That handles all of the enemy movement and things, and it also draws the player and things back to the screen. Now that's all common code. That's not platform specific, so that's in the common section. And finally, we loop all the way back to the top up here. Okay, so that's all of the logic code that's in this platform specific section. Here's the clear screen routine. We just select the screen memory, which is in chip RAM all the way down here somewhere. Here it is, and we're just going to zero all of that. Now the screen is 320 by 200 and there's 2 pixels per byte, so we're just using that formula there, and that will clear the screen for us. We're using CLDIR0 here, which is a function I use for zeroing an area of memory. Okay. Now here is the routine that draws the characters. Now the characters are actually in the same format as the bitmap data here, so we're using our sprite routines to show the characters to the screen, but we need to calculate the address of that character. Now the first 32 characters of the font aren't represented, so the first character is space, so we subtract 32. We then multiply by 32 because there's 32 bytes for each character in the font, and we then calculate the offset within the font data for that character. We're getting the XY position here. We're multiplying the Y position by 8 because there's 8 lines per font character, and then we're using the show sprite routine, which will show that sprite to the screen there. Okay, so show sprite will do the work for us there. Okay, so that's the font routine, and now we're going to be looking at the sprite routines, which of course is being used partially by this routine here. Now the blank sprite routine will take an object off the screen. An object has 8 bytes that define its definition in the game. Now the first one we're looking at here is the offset collision program, which is it's how the object interacts with other objects. So does it hurt the player? Is it a power up? If it's over 250, however, then it's not in play. 255 is an undefined object. 254 is a dead object. So we're just checking if the object's dead, in which case we don't need to draw it. If we do need to take it off the screen, if it's an active object, we're using the space of the font to do that. So that's just being used as the source data. And then we're going to jump down here to actually draw the sprite. Okay. Get sprite address, if you remember, calculates the offset of the animation frame for the sprite. So we're masking off the bottom byte here, just because we are using a single byte to define our sprite number. We're then multiplying that by 32, and that's going to be the offset of the sprite within the bank, but we need to calculate the bank as well. So we're taking the sprite frame here, which is an auto-incrementing object from 0 to 3, and we're selecting which of these banks we want to read in the sprite from. So we're doing that there, and that will calculate which frame of animation to use. So this is doing the entire job there of calculating the source address for us. Show sprite will show a sprite that's defined by number and the X and Y position are specified, and that's used by that tile introduction routine. Do get sprite object takes all of the settings from object A4. That should be an A4 there, not an IX. A4. IX was the original Z80 version. Okay, we're getting the sprite number here, and we're getting the X and Y position, all from the object definition here. And then we're calculating the screen pos using get screen pos, which we saw in the simple series. That's been copied as is from that series. Okay, here's the routine to draw the bitmap to the screen. We're copying all 4-bit planes. This again is copied straight from the simple series. I don't think it's been changed at all. So that's over there if you want to see how that works. Get screen pos is calculating the memory address of a line and a byte of the screen. You can see here we're multiplying the line number by 40 because there's 40 bytes across the screen. Now there's 4-bit planes, remember the bit planes are separate, which is why we've got these huge additions here. So there's all of the first bit plane, second bit plane, third bit plane, fourth bit plane for the screen. So we just add 40 to move down one line within a bit plane. Okay, that's what get screen pos does, calculates a screen address. We've already discussed player read controls dual. Wait for fire is the pause in between levels. We wait for the fire button to be pressed and then released. And while we're waiting for that, we just re-initialize the random number generation. We've also got a wait vblank routine here, which just tests to see if the screen is in vblank. And that's, I believe, only used at the start of the game. It's just a simple delay in this game. It's not using vblank really. But we need to wait for vblank to start the copy list up. Then we've got our sprites here and our font, just there. The common code here, which is used by all the 68,000 versions. That's the things like the game logic for moving the enemies around, things like that. We've got some definitions of the variables here, which we covered in the previous lesson. And then we've got the chip RAM settings here, the settings for starting up the screen, the memory for the screen memory, the copy list for handling the drawing of the screen, and our sound samples for chibi sound. And that's really all there is to it. And there we go. So that's the YQuest game on the Amiga. You can go to my website and you can download YQuest and you can compile it and play it yourself. And of course, as I always say, if you want to and you can make any use of it, you're welcome to use the code as any kind of foundation for your own game. And if you somehow manage to sell it, all the best to you. You don't need to give me credit. I don't care. So you just do whatever you can with it and make use of it. Anyway, I hope you've enjoyed this. If you have, please like and subscribe. If you like the videos, then YouTube recommends them to more people. And if you subscribe, then it encourages me to make more videos. So that helps everyone out. But whatever you do, I wish you all the best with your Amiga programming. Thanks for watching today, and goodbye.